Oh, and that's annoying, that little spot there. So I'm gonna try switching the display in here to this one. And I'll have to put in a ticket for that little mark there. So there's just unfortunately going to be this little audio toast here in the middle here. So but we'll have to deal with that today, but I don't think it'll be a major issue. So I'm Ted Pavlik. This is IEE or CSE 598 Bio-Inspired AI and Optimization in spring 2026. So just today I want to go over a brief outline of the course, policies for the course, and start us off with some motivations for first kind of technical content, which we'll start into a little bit at the end of this session today, and then launch into that more on Thursday. So I recommend taking a look at Canvas. So everything has been recently added to Canvas. You should all have access as of this morning. And one of the key things to look at there is the syllabus, which a copy of here. I'm just going to highlight a couple of things, and so you can read all the details there on the online version. So we'll get more into the course description as we go here, but basically speaking is when I came to ASU, I noticed that there were a lot of methods that I knew that were, or for one, there were a lot of optimization metaheuristics for one that are used in industry that are well understood in certain communities that we didn't at that time have a lot of courses that discussed. And so there sort of felt like there was a need for that. And then also there are a lot of technologies that we use that come from an inspiration from either the physical, well, from some aspect of the physical world, and that includes physics, but also includes nature. And so wanted to sort of drill down into those, and because from there, think that we might be able to, as we look forward with new technologies, might be there's new opportunities there under the latent opportunities that we might have an opportunity to exploit. And so trying to then connect to some of these inspirations so we can see where they come from and maybe where else you could take them based on their kind of home discipline, what movement has happened there, and seeing if, well, in their kind of this model discipline that takes from them, is there opportunities for similar sorts of movement. So that's kind of the motivation for this course. This course is it's approved as an elective, an OR elective for IE, and it's an elective for CSE, and for RAS, it's an elective that can be counted towards the AI concentration. Those of you that are in a master's program that have a portfolio, gradually a lot of master's programs are sort of getting rid of we're not getting rid of the portfolio, but de-emphasizing it. Now that totally 100% course-based options are available, but there are still some master's programs like the RAS master's program that still don't have the course-only option, they have the portfolio option, and this is a course where there'll be a project that meets the requirements for that portfolio. So you can use this project toward that portfolio, so that's an option for you there. The main format of this course will be through this in-person lecture attendance. I'm not going to take attendance credit, and as much as possible, as much as the technology allows, I will record these lectures. And so if you're keeping up, how you're keeping up, that is kind of up to you. I do appreciate seeing everyone here. I do appreciate the questions we get in class. I have made this a lot of flexibility throughout the lecture so we can go in different directions so that and still get everything done at the end of the semester. And so the more people that show up, the more opportunities we can have for that back and forth. But if you can't, I know life happens. Then as much as possible, as much as the technology allows, I'll post these on the Canvas webpage. And so that's the idea there. So and I'll also post all of these whiteboard type notes that I'll take here. That will be posted as a PDF alongside those lecture notes as well. So everything that we do in class, I'll try to make sure gets posted to Canvas. Again, unless there's some technical snafu, like that, weird glitch that's happening whenever I share from the normal screen that I shared from. So otherwise, for instructional staff, This is a class that's under 50 students, which means it doesn't get a TA. It only has a grader, so there's just me and a grader. So because of that, if you want information about the grader and about me on Canvas, right on the front page of Canvas, there's an instructional staff page. It's also linked under modules. And from that page, you can find information about how to contact me. And also, I haven't posted my office hours yet. They're still TBD, but when I set those, then those will be set there. You can also find information on how to get in contact with the grader. So difference between a grader and a TA is that a TA can provide additional office hours and help with the course in general. A grader you only reach out to for questions about the grade. So there are several assignments that we'll talk about here. And so the grader will be, if you have a question about points that you miss, then you can reach out to the grader. But if you have a question about the general content, how does this work? Those sorts of things, then reach out to me because the grader is only paid to do the grade. So look for that for those office or those hours there. Otherwise, mainly administrative stuff here. For reading materials, anything that relates to reading that relates to the content of this course, I'll provide for you. So I do have a couple of suggested texts. So there's some auxiliary texts that I suggest, and I'll actually use the library resource manager thing in Canvas to try to make those available. I think at least one of them is available as an online text from the library that I can try to make an easy link to. But those are just auxiliary. So a lot of the topics that we talk about, you might be able to find interesting information that will help you with, say, mini projects that you're doing and so on. But theoretically, everything you need for this course will come from the lectures and from PDFs that are posted within the modules that are on Canvas. So that's what we kind of talk about there. So what are we going to be talking about in this course? And so this is the basic structure here. So usually we get through these 7 units, which I'll talk about here in just a second. And then if we have a little bit of time at the end, then we at least get 1 or 2 lectures on Unit 8. Rarely do we get to Unit 9. But the way the flow here is up top here is we talk about optimization. We sort of introduce optimization. And this is often from the genetic algorithm perspective to start with. And then from optimization, then we'll talk about how you can pivot from optimization and then start doing things involving what I call creativity here. So how do you do more open-ended generative things with these bio-inspired methods? So that's when we'll learn about only genetic algorithms, but immune system inspired work. So this is stuff that now people like Stephanie Forrest, who's a faculty member here at ASU, she is very well known that she built her career on these sorts of methods. And so if you've ever had any interactions with Dr. Forrest, then the type of content we talk about in Unit 2 would be stuff that she would love to talk to you more about. So we'll introduce those types of methods, and then we'll go into multi-objective optimization. So we'll talk about game theory, we'll talk about Nash, we'll talk about Pareto, how those things relate to community ecology, and how those relate to optimization algorithms where you have multiple objectives. So, if you've got multiple things you're trying to optimize at once, you don't have one single solution. How do you deal with that? And so that's what we'll kind of open up in there. And then we'll move into distributed methods. And so this is going to get into kind of swarm intelligence, happens here. We'll start to flirt with that. We'll actually cover swarm intelligence more formally down here. So this is also kind of swarm intelligence light. And then the full swarm intelligence comes here in Unit 6. So what we're going to start talking about is now that we've had this genetic foundation, then we start looking at how do we solve these types of algorithms in a distributed way? And is that just a refactoring of the way in which we'd solve them without distributed architectures? Or does it allow for qualitatively different solutions? And so that's what we kind of starting to work in there. That will end up opening up us to talk about switching away from nature for a bit and going to physics. So then in unit 5, we'll talk about these physics-inspired methods, which if you're familiar with things like softmax, that is sort of an important function at the kind of the back end of a neural network. This is where softmax comes from. And then other things like max-int methods for more classical natural language processing comes from here. So this is an opportunity for us to define the concept of entropy and talk about entropy in physics and what does it mean, entropy in information theory, what does that mean, how those things help inform algorithm design, and how that's left a mark on a bunch of things like Markov chain Monte Carlo sampling, which some of you might be familiar with if you've done any sort of Bayesian statistics, but also neural networks and so on. So it's a pivot away from nature into physics, and then we go back to nature in a very different way, where we formally go into full kind of swarm intelligence mode here, where we're going to talk about ants, we're going to talk about bacteria, and we're going to talk about flocks. So the three things we mainly focus on: ACO, BFO, and PSO, which are very different ways to do this optimization, and that you can use for, and then why we might choose one of these and not some of the things that we've talked about earlier. So what types of problems are better suited for ant colony optimization instead of genetic algorithms, and vice versa. So that is that. And then we flip to, kind of more contemporary, I don't want to say more contemporary topics. All of the topics that we talk about here, there's still lots of people interested in these topics. There's lots of people using them. We're going to talk about, why, if those of you familiar with training neural networks, you'll already be familiar with certain methods, which look like they're in competition with some of the methods that we talk about early in the semester. And so, but we're going to define it. Well, it turns out the neural network is sort of a simpler, training a neural network is actually reason why we have those. So, I'll end up giving a lot of these, these references to neural networks just because there's a lot of students familiar with that. Well, then actually, because a neural network is itself bio-inspired, have a pretty large unit in unit 7, where we talk about where the neural network comes from, all the way up until kind of modern ways we're using it now. So, the classical way to talk about neural networks is supervised learning, which we'll talk about more formally. So a lot of you are probably familiar with that term, or familiar with those ideas. We'll give kind of a very quick refresher. Nowadays, you can take a frozen network like ChatGPT, you give it a couple examples, and then it can hopefully generalize from those examples. So it's almost like it does this zero-shot learning without any training going on whatsoever. And how does that relate to psychology, models from cognitive science, and so on? So what is in the motivating now what we know about nature to come up with new ways to use these modern neural networks? Those will be things that we'll start to touch on there in this unit 7. And then if time permits, then that's when we go into a little bit more complex systems. So we'll introduce cellular automata and there are evolutionary versions of them, so they can become substrates to enhance some of the tools that we've learned about earlier in the semester. And rarely do we get all the way to here to unit 9, but it's possible that we'll end up talking about a little and how those are impacted by some of these things. But I will frequently, for those who are in robotics and automation systems, a lot of the stuff that we talk about earlier here come from thinking about automation systems. And I will make references to robotics this semester. All right. So before now the next, the next maybe 10 minutes is just going to be policy stuff. But I want to pause to see. I mean, a lot of the I can pause for. Yeah.
Are we going to have simulations of these algorithms as a project work?
Yeah, I'll get into what the project work is. So you'll be to do mini projects where you'll implement these things and try them out, push them and learn about them. And then there is a term project at the end where the project on. So I'll talk about that in a moment. And in each one of these units, in the modules in these units, I've provided a lot of resources, and some of them are textbook chapters that give other examples. Some of them are links to software. So hopefully that question will, more of that question will be answered in a second. Yeah.
It's just a general question about the class. Would you ever allow like students to join in on the Zoom call?
Capability to, but I do want to give people the incentive to come to class. I don't provide extra, I don't check for attendance. So the only way that I can provide you incentive to come live is to give you that opportunity to see it live and ask those questions live. So that's what I kind of use that. But a little while to code that. Once it's available, I'll post it. So usually same day, the asynchronous version will be available. So if you miss a class in the morning, probably by 4 p.m. or definitely by that evening, you'll be able to watch it, which comes in anyway. So maybe that's just as good. Yeah.
What unit or topic are you personally most interested in or most passionate about?
It varies. I mean, a lot of these are things that I've worked with throughout my career so far. And, a lot of times it's been following my interest at the time. I think I'm the only I'm slime bolts. I have a couple of grad students who work in Panama and Costa Rica and then Australia doing field work with ants. And so I do a lot of work with ants. More closely related to a lot of things I've been doing in my lab. But on the other hand, the things that we'll talk about in swarm intelligence are going to be much more classical models. So we won't be, I might link to maybe some papers of mine in the module, but I won't be talking about that directly. So on one hand, a lot of my CS students are working on are much more in this unit 7. And I've actually lately becoming more interested in not just, so I do a lot of work with neuromorphics. So I work on a project right now where we introduce the concept of sleep to neural networks. A little bit of that on that here. So that's down neuromorphics. So how do you get artificial neurons that act like real neurons, not just act like mathematical functions. Network with billions of parameters, then you stop thinking about it, just like you stop thinking about the brain, it's a combination of neurons, you start thinking about it as a cognitive entity. And then you start thinking about, well, so what are the cognitive modules of an artificial neural network? And that's stuff that I've been doing a lot more with my grad students. And so I'd say that but I've always had a soft spot in my heart for genetic algorithms and multi-objective. And I was a grad student where I was focused on multi-objective So this will be an area talking about that, and it's linked to community ecology, will be something that's exciting for me too. So, I mean, it's all, I mean, I put it in the syllabus because I think it's all important and that's, you know, it's where I would be very excited to teach about. But, so it's hard for me to choose a favorite, but, you know, I'd say that it just based on recency, I'm probably gonna have the most recency. And then there'll be a lot of the examples from my lab that will come up in this.
Simulating what happens in nature in computing, like I remember in Japan, they had this amoeba slime thing.
Yeah, if I saw him, all these stuff with, yeah. That's sort of the rail network and a number of other, we will talk about that when we get into swarm intelligence a bit, but we're not about, this course. Natural systems so that we can build better models for engineered systems. And so there will be some back and forth, but the main motivation here is these use computers to do complex optimization tasks or use artificial intelligence or develop new algorithms that will be useful in ways in which they're very different than the way we normally solve things. Can we understand those different ways and can those enhance how we're doing? And you might be able to apply an engineering or a computer science mindset to thinking about natural systems, and I think that'll be productive, informative, but I guess we know a little bit about nature, how can we use that to enhance what we do as engineers and computer scientists? Okay. So how do we have things divided out? Let's get a refresh here. So so there will be 5% of the course grade are what these called these muddiest point reflections, and I dropped the lowest two of them. So every week I ask you to go to a little Canvas activity. Words there. It doesn't have to be a sentence, it doesn't have to be a paragraph. It's just of the topics that we talked about that week. There might be multiple units. That might be the end of one unit, the start of another unit, which is of the do you feel you was the clearest to you? And then the second question I ask is which of those topics was the muddiest? Now you might say of all the things you understood, which of the things is kind of like the least, or you understood the there. And then there's a third question, which is basically, is there anything you heard from this week that was so exciting that you'd be really well, everything was fine this week, but there's no topics that I'm really excited to learn that I hope that we talk more about. And so or you can write me a couple of sentences. I will then do my best to reflect to have a muddiest point. I just really didn't understand the difference between Pareto optimality and Nash optimality. Can you to recover that or to post something? But if there's a couple of people out there, I don't want to feel like you end up getting lost. that question too. And I will try to use the muddiest point as a way to just speak to you and say, okay, so here is a be some nice just-in-time feedback about how things are going. So that's why I ask you to do those, but I know that it's annoying. I also have these unit concepts checks. So like I said, there's about 7 or 8 units. One short auto-graded, well, except for the first one, auto-graded Canvas assignment that just make sure that you caught those things. And then we've got these mini projects. And so for mini project 1. So basically what this is, you know, they don't give us much and so for each unit, I want everyone to have an opportunity to say, you know, I really like the topics here. This would be a short project where you demonstrate that you can implement the, you know, an algorithm from that class. A report of your results. If I had everyone do that for every unit, not only might it be burdensome, that's why I basically give it sort of your option. So the intent here is that everyone two, maybe 3 of the other mini projects throughout the rest of the semester that you want to feel like, even though everyone will see that due date on Canvas, don't feel like everyone is expected to do. I have is a half grader for this course, so it's you know there's not. So it's a way to kind of balance the resources there, but that's why there's so many of these. Where, you know, given the 7 units, you're basically choosing 2 or 3 units in addition to the first unit where you're going to and then there is a final exam, which is going to be take home. Book or open notes. And then speaking of projects, then this final group projects. So we've got about 45, 44 or so students. So groups. So each group will choose will find an algorithm, a bio-inspired algorithm that semester. So it might be a major elaboration of an algorithm. So instead of particle swarm optimization, is based on a natural principle, but it's not one that we've talked about in class. And you work with your for that algorithm that you could then write up as a 4-page extended abstract in IEEE. I'm not going to ask you to submit, but you imagine you might submit somewhere as sort of a demonstration of an algorithm, as if you were this class to use these algorithms to do something novel in their own research, and then they actually do spin those off into something that they submit to for that, definitely will support that. But otherwise, just basically using that to do a more significant version of talk about directly in class. And that is, overall, that's 40% of your grade, which is why it's important. In that, like, you get 2% of that, of that 40%, so not 2 of the 40. Who's your group name? So that will happen. I'll remind you of the due dates for these, but these basically happen mid-semester. And so around mid-semester, you and your group mate will submit as a group assignment what algorithm you're planning on doing, and you're not tied to that. So like a 2-paragraph proposal, which says, this is the algorithm we're doing. I've demonstrated set, and we're going to study this particular problem. We're going to apply the algorithm in this way. We expect to get these types of results. And those you're going to do a 10 to 12 minute presentation with your group mates. You're upload those to Canvas so we don't present page extended abstract. Now, the way, rather than having all of you present those presentations here, I have to watch everyone's presentations, but you still guarantee that you get, several eyes, So I'm going to try, I used to use Canvas, which has a lot of technical limitations to its peer review, so that you now harmonize, a new tool that we have access to, that kind of beta testing for this. And so that means student will be assigned a small number, maybe 2, maybe 3 presentations and reports where some comments, and that kind of takes the place of us all sitting up here for a week and a half listening. These deliverables will be due Wednesday of the last week of classes, and then these peer week, then that's when technically this take-home exam will be due. And all right, so that's the basic structure there. Any questions about that? Unit tests or anything like that. So it will be based on the fundamental concepts from the course. Some multi-objective utility function, find the Pareto optimal solution. Just more kind of core understanding of the concepts you need, that if you ever come across a bio-inspired algorithm, you'll be able to parse that. Okay. So what else do we got here? All of the details that I just talked about are written out down here. So make sure that to take a note of that. Final project, like I said, team project. That's normally what I do for this class. And again, so all of this stuff at the next page of this talked about. So once it refreshes, top of that page, grading scale at the bottom. We do have undergraduates who will take this course. I use a more undergraduate. Again, just to be a little more consistent with some of the undergraduate courses. Otherwise, late. That I've got here. Assignments you're going to see are going to be due at usually like 11:59 p.m. one day, but they're available after 11:59. Canvas might mark it late in the grade book, but you can ignore that. Or whatever, it's just a grace. So it'll be to get on your calendar, it'll be due at 11:59. Actually, 10 a.m. the next day. So if you get it in, you don't need to email me and say, oh no, you. The only exception to that is the final project because of the peer review mechanics, and I might be able to make this. In Canvas, when I use Canvas-based peer review, and in that case, I really had to get everything in Wednesday. Project is one of the few ones where there is not a grace period, but pretty much everything else in the exam in the class. And that's I'm just mentioning there about the final project is a special case of that. Grade corrections. 40-some students, but we only have half a grader, so it does take a while to do this sort of grading. So got a week to review it and then come back and say, hey, I think I might have maybe this was misgraded. But then after that week, team then submitting all of that because it ends up being we're already worried at that point we're about final. That's when it starts the clock where then see that if you see you got the grade in Canvas. If you email, this is the primary way I communicate is by email. I'll also use Canvas announcements. Those notifications as well, or as quickly. But if you email, then please prefix your subject. Really appreciate that if you do that during those correspondence. Otherwise, generative AI, I have to mention that now. AI to do basic proofing, those sorts of things, but I really want the content of anything you submit to be algorithms that you can try. That sort of brainstorming is okay, but when it comes down to actually doing the implementation and doing the writing, then I really want you to limit your generative AI to just I'm not going to be going over with a fine-tooth comb of every submission to see, does it look like it has where it's pretty clear that no effort was put into it. So, really try yourself first. represents your individual effort and not the effort of a pre-trained model. Just to get this out of the way, I'll mention that, so there's all of the academic integrity in their expectations on students, which will pop up here slowly. I know that I got an 86.2%, but if I just got an 87, it would round up to do with a fellowship or whatever. And ASU's got this policy that if you request a violation, and I'm then obligated to report it. So it's totally fine if you're in that way. Those definitely let me know. But do know that if you know. I hate that to say that, but it just comes up, every semester. So that but I do need to mention that there will be group work and things like that if issue to know. If you do bring that to my attention, because as a employee of the university, I'm a mandated I have to report that up the chain. If you're not comfortable with that, then ASU Counseling Services has a special case where they are not mandated reporters and they can handle that in a way that up. Of course, you should bring those sorts of things to me if those sorts of things happen. Up. Otherwise, students with disabilities, sales, it's no problem accommodating sales. And then we can talk about how to make that combination. Otherwise, recording devices, I will provide anything that I provide to you stays with you, so don't upload it to any other sites or anything like that. ASU considers it academic misconduct to sell your own notes or to publish your own notes on these other sites and so on. So please don't do that. That's all of the main policy things. So I do want to say a more technical thing or up for our next lecture, but before I get to that, any questions about the policy stuff, about the structure? All right, okay, so let's then this might an other system here that's a little faster that makes this a little bit more realistic, but we're gonna have the curious if this is refreshed here. Surprised this guy hasn't yet. And so this first unit is going to be introducing us to genetic approach category of so-called metaheuristics. So key terms that we will introduce, or these terms are the notion of the notion of heuristics, the notion of metaheuristics, and hyperheuristics. So I'm a little surprised this is quite so slow. Classroom, and it's definitely is not this this slow. So working on that. But yeah, heuristics, metaheuristics. So we want to define what these terms are, so we kind of understand these things a little better and try to understand. The old school whiteboard here, and until we have something that is a little more realistic. So maybe I'll do this. See, maybe I'll get lucky, and no, it's just really they're both just bad. Okay, so maybe I'll maybe I'll get lucky and things will pick up too. And but so let's consider that out here, and I would call the ego vehicle or vehicle we're focusing. Is what following distance should you come up with? Little whiteboard. Let me make sure that I'm covering all of the things that I know. All right. So if you if you're too far away, what are the downsides? What happens when you're too far away? Are there upsides and downsides? What's the problem with this? Like, why do you not just want to be infinite? So this might be, too slow. If you're long time to destination. So that's bad for you. But what's the upside? So that's good. Too close, then you're getting. So this shows that there is. how do you, our question then here is, hey, how do we navigate this trade-off? How do we design? And so theoretically speaking, you might be able to build a utility function which models. Again, just maybe, and I got lucky, and this is. So if we were to build kind of like a fancy word for happiness. There's this bell-shaped function where we have our distance. Our utility here. And maybe it looks something like this. Some theoretically perfect following distance that I can call d. Two concerns. Theoretically speaking, that might exist. But in reality, and so we're probably just going to be happy enough if we can get above is going to be good, which means any following distance in this range. So we'll call these good enough. Good enough are going to be what we're defining as heuristics. A heuristic allows us to produce a good enough solution, a solution. So almost definitely not the optimal solution. And so, you know, one heuristic might. What's the 3-second rule in driving? Make sure there's 3 seconds between you and the car in front of you. So if that car has strategy, because at slow speeds, it allows you to get closer to those cars, and at fast speeds, you get far. This optimal speed or get a lot pretty close to it, but it's almost definitely not the optimal speed. A 1-second rule, you're going to be pretty close. But like maybe 3.5 is not good for other reasons. Like maybe implementation of the time. So there's all sorts of reasons why some parameter choices might not be good or better, or might be better than others. Another level of optimization. So the heuristic is trying might be the 3-second rule. This might be the 3.5-second rule. This might be artificial neural network. And so it doesn't have to be something that it could use any weather, data about the terrain, all sorts of things like that, and coming up with a general following. Say that that particular policy is best. It just tends to perform. The 3-second in on dry land rule, but a 4-second rule in the rain or whatever. Well, that modification. Point is, with all of these heuristics, any one of these rules that you come those parameters. And that is the notion of a hyperheuristic. So you could say that I have a family of heuristics called the n-second rule. And then the question is, then how do you find n? And physical theory that informs what that should be. But you probably don't. A car under ideal conditions, you might be able to solve for, what might be the optimal number. We use to parameterize heuristics are called, metaheuristics. Our next step is so metaheuristics. I apologize. The